Hello everyone, my name is Richard Fung. I'm the CEO of the Semiconductor Inc., a subsidiary of OpenEdges Technology. Today, I'm going to talk about the design challenges for LPDDR5 and DDR5 and the need for flexibility in the IP design. Let's take a look at the topics that I'm going to cover in this presentation. First, a bit of introduction to OpenEdges product lineup for those who are not familiar with technologies that we provide. Then we'll have a brief introduction of DDR5 and how it works at the high level, and go over some of the features of LPDDR5 and 5X memory subsystems. We'll also take a step back and take a look at the strengths of LPDDR5 and 5X when compared to GDDR6 and HBM3. We'll then dive into OpenEdge's PHY development philosophy and go into details of our PHY architecture and our differentiations. We'll conclude the talk on our LPDDR5 availability today. So let's dive in. At OpenEdges, we have primarily two main product lineups. Our Orbit line of products is our total memory subsystem. It starts at the interconnect bus called OIC, connecting to the DDR controller, the OMC. Finally, our DDR5, the O5, acts as the physical and electrical interface that communicates with the external DRAM. Each piece of these IP can be licensed separately or altogether for the most synergy in the memory subsystem. Our Enlight line of products is our AI processing unit IP, a neural processor also known as an NPU. With the Orbit and Enlight products lineup, our customers can license a group of IPs enabling integration of AI seamlessly. So this talk today focuses on the DDR5 products, so I thought I would give a high-level introduction of DDR5 for those that are not familiar with its role in the memory subsystem. Effectively, the DDR5 is the electrical interface between the memory controller and the external DRAM. Today, the DRAM can be mounted on a silicon interposer, on a packaged substrate, soldered down on the PCB, or it can have a DIMM form factor that is plugged into a DRAM socket, depending on the DDR standard. So the DDR interface remains to be a high-speed single-ended parallel interface today. It utilizes the command address bus, also known as a CA bus, to issue commands to the DRAM. Note that the CA bus is a unidirectional interface, so the DRAM cannot directly respond back to the DDR5 through the CA bus. And with the commands and addresses issued through the CA bus, the DDR5 has to send TX data or capture RX data at exact cycles based on the set latency. So this is what makes a DDR interface unique. The cycle-accurate interaction of the memory controller and PHY with the DRAM devices operating at high frequency. And with multi-rank systems, where there are effectively more than one DRAM device connected to the same DDR5, the overall memory capacity increases, but it is at the expense of loading on the PHY. So each DRAM connected to a dedicated chip select signal is referred to as a rank. Now let's take a deeper look at what the LPDDR5 5X has to offer today in terms of features. First off, as a low-power memory standard, it utilizes a low VDDQ of 0.5 volt for its high-speed I/O supply, greatly helping lower the power envelope. LPDDR5X is currently the latest published JEDEC standard for low-power memory and has a maximum data rate of 8533 megabit per second, representing a 33% increase from the LPDDR5 standard's 6400 megabit per second. As the physical channel remains relatively the same for platforms that use LPDDR memory, the increase in speed does represent an electrical bandwidth challenge for LPDDR5X. That is why it has added an optional per pin DFE feature to help enhance the receiver margin at the DRAM. LPDDR5 and 5X is a very high capacity DRAM type for use in solder down applications, with 128 gigabit packaged parts available today. Now, for those that are trying to determine the DRAM type to use for your SoC, let's look at and compare between LPDDR5X, GDDR6, and HBM3 at a high level. Overall, looking from spec perspective, HBM3 thus represents the DRAM of choice for maximum bandwidth and energy efficiency. However, it does have a drawback for higher design complexity for the overall system, as well as higher NRE costs. From production perspective, it has a higher test cost and it can run into supply chain constraints due to limited manufacturing capacity. Of course, there are many types of high performance systems and applications that demands the absolute best, then HBM3 is the way to go. Now, with LPDDR5X, it is the next best choice for maximum capacity and lowest cost. And you can extend your overall system memory capacity by utilizing OPENEDGES PHY to only find a market that supports up to 4 ranks. GDDR6 is a very high bandwidth memory that is more cost friendly to deploy than HBM3, but only comes in lower capacity devices, but has a highest power envelope. But it does have its place in some class of high performance systems, such as GPU or some AI SoCs. Finally, DDR5 offers the most memory capacity, but are used in DIMM form factors that will require a platform to be like that of a motherboard. So it's out of our comparison for memory subsystems that can be used in soldered down environment in either a space congested platform, an adding card, or consumer's electronics products. So to the right, we have a spider chart comparing the 3 different memory subsystem types based on 5 different metrics that system designers would consider. Here, we're looking at the memory bandwidth and capacity, the PHY area, power efficiency, which also translates to thermal efficiency, as well as a cost implication. So this is just a one-page conclusion summary of our comparison. For details of this analysis, please contact our sales team to arrange a more in-depth meeting. So let's take a look at our PHY development philosophy. So we get this question all the time. How do we compete with the bigger companies? What are our differentiations when compared to our competitors? So since day one, our philosophy has been to develop the latest DDR standard in N-1 or even N-2 technology nodes to differentiate ourselves, while our competitors are developing in the latest technology nodes. So we believe by developing in mature tech nodes, customer using these tech nodes for their SoC and mass production can also get the benefits of the latest DRAM technologies. So with chiplets being the next big thing in the semiconductor world, our strategy also plays very well into this ecosystem. If we look at how other builds chiplets, their I/O die are often manufactured using a more mature tech node, while only their core compute die use the latest fabrication technology. Well, our product offering provides the latest DDR technology in mature tech nodes. So folks looking into building chiplets can benefit from the reduced cost and higher yield of mature nodes, while continue to benefit from the latest DDR technology using OpenEdge's PHY. Let's take a look at what OpenEdge's latest LPDDR5 X5 has to offer. So first off, we support multiple LPDDR standards, from the latest LPDDR5X backward compatible to LPDDR4. So depending on the cost performance trade-off of your system or your family of chips, a single PHY can handle them all. Note that not all DDR5 vendors supports back to LPDDR4 standard, which has a higher VDDQ supply voltage of 1.1 volt. But we're providing this flexibility with our PHY design without any negative effects on PPA. Secondly, each of our PHY channel can be flexibly constructed to have DQ width of 8, 16, or by 32, with support of multiple ranks per channel, up to 4 ranks. Our PHY supports multiple frequency set points, also known as FSPs, so that various frequency states can be pre-trained and restored quickly for power optimization. A PHY has a built-in microcontroller, which I'll go into a bit more details in the next few slides. And with this, we have firmware-based PHY independent training and DRAM initialization, which does not require involvement from the memory controller at all. For production tests and diagnostics, different firmware can be loaded to exercise a PHY differently from its normal mode of operation. Now, last slide, I talked a bit about our PHY's microcontroller. Let's take a look at the flexibility that we can get out of having a microcontroller inside our PHY. So with firmware-based training using a microcontroller, we can tune a training algorithm and optimize it based on the platform. We can change the data pattern being used for training, reorder some of the training steps, as well as control the relative timing in performing training. A microcontroller also has an ALU inside to perform arithmetic operations. In calculating training results, operations such as averaging, weighted averaging, adding offsets, etc., all come very handy in tuning the training algorithm for optimal results. This is especially true when trends are shown in silicon measurements that require arithmetic correction. Now, training is just a sequence of operations. The control of when to train, how often to train, and dealing with not on-demand training requests are the devils in the details. A microcontroller also accommodates these required flexibilities, having various forms of dynamic training triggers. It can be an event-based trigger of retraining, or it can be periodic performing partial training, either in the form of incremental training and or fractional training. So let me introduce you to the architecture of our proprietary microcontroller called a PSM, which stands for Programmable State Machine. The PSM was architected by our DDR5 architect with instruction set that are tailored for DDR5 training and controls, with a high level of parallelism in operation. It has a custom instruction set with 64-bit instructions, and there are about 60 instructions in total today. To handle dynamic triggering, there's an external event control for breakpoint insertion and event synchronization. On PHY hardware control side, there's a custom interface designed to communicate with dedicated training hardware. There is a built-in ALU to perform arithmetic operation. And with the CA interface, the PSM can perform real-time timing control, DRAM initialization, and essentially full control of sequencing any command with any spacing to the DRAM. So aside from the PSM, our PHY also has what is called a micro PSM, which is a reduced set of features from the PSM. You can think of it as a small core microcontroller. So it also has a set of custom instruction set that are 32 bits wide, with about 20 instructions in total today. It essentially has a CA interface removed, as well as a smaller ALU relative to the PSM. Now let's take a look at how the PSM and micro PSMs can be used together. Together, the PSM and micro PSM are used for all hardware algorithm needs within the PHY. The simplest usage would involve one thread per PSM and micro PSM. We can utilize PSM and micro PSM in parallel for concurrent processes to minimize the processing times. They're used for calibration, link training, monitoring, as well as event control between the PHY and the memory controller. Next, let's take a look at the physical construction and integration of OPENEDGES LPDDR5 X PHY. The PHY is made up of the soft IP and hard IPs. So illustrated in this picture, the soft IP is delivered as RTL, and highest frequency clock in the soft IP is the DFI clock. The dimensions and physical design can change based on customers' configuration and requirements. The soft IP talks to the hard IP, which is made up of a collection of paths, lanes, and macros. The C group and D bytes are not hardened into a group, but instead they're delivered individually for maximum flexibility based on the customer's bump arrangement. So we understand that RDL bumps and BGA ball out can be very different between different products. So flexibility can help with optimal signal routing on the package substrate. What we do is once we know the relative hard IP signal ordering, we can help our customer with an instantiation depth so that they can read it in and have all hard IPs placed automatically on their SoC floor plan. So this would remove any complications in placements, placement orientations, abutment signals, etc. So essentially, to the customer, once a def is read in, the entire hard IP group is placed as if it is a single macro, without the need to fiddle around with the placement further. Now let's take a look at a higher level how OpenEdge's LPDDR5X5 differentiate from some of the other vendors in the market. So from a digital implementation perspective, there is only a minimum set of timing constraints and special layout requirement, and it's easy to close timing on DFI clock or lower frequencies only. So there's no other higher speed clocks that are required to close timing on. So for some vendors, the place and route blocks include high-speed clock domains with many timing constraints and physical constraint rules. So this is actually a customer feedback that we got. Full silicon flexibility. We've taken a look at the PSM and what it can do. It allows us to alter training algorithm and sequencing without the need to respin the silicon. For any vendors that do not have a microcontroller, the ability to change is limited. So with the PSM, it also eliminates the need for external compute resource requirements. Without a smarts inside the PHY, system compute resources are required to monitor the PHY and the DRAM status. And finally, what we all really care about for production is the DFT coverage. Because all our hard IPs are contained together, not instantiated in bits and pieces inside a soft IP, we maximize the scan coverage with very little timing exceptions. Some vendors instantiate hard macros in the soft PHY or soft IP, which can reduce scan coverage and also introduces more timing exceptions. So what else we offer to our customers that are also differentiations? We believe strongly in providing support and flexibility to our customers, and we believe these are the key to our customer successes. And to us, our customer successes are our successes. Our applications engineering team are all dedicated DDR5 AEs. So the first person you get in touch with is not just a general help desk person, but our experts in DDR5 support. And when the scope of the problem are more in depth, our AEs have direct access to our designers and architects for solutions and answers. Remember, our support team and experts are here to help every step of the way to your SoC's production. And from physical design planning, such as floor plan, bump map, to BGA ball map and package substrate reviews. Or during digital implementation, we're here to help with timing closure and reviews. In bring up and pre-production stage, we're here to support you with firmware changes and updates based on your requirements. So let's take a look at our DDR5's availability. With LPDDR combo PHYs that supports up to LPDDR5 or LPDDR5X, they're available in TSMC N22 for LPDDR4, down to our latest TSMC N7 for LPDDR5X. We're also in the process of porting to TSMC N6, which is very similar to TSMC N7 techno. In the Samsung Foundry process, our LPDDR5 for combo PHYs are available in the Samsung 14, LPP and LPU, as well as 5nm LPE. For HBM3, we have taped our test chip to TSMC N7, and it can be ported to TSMC N6 quickly upon request. Finally, we also have our GDDR6 and TSMC N12 technology node. So in conclusion, we encourage you to reach out to us to discuss about how OpenEdge's memory subsystem can be a fit to your next SoC. We're here to help you with your next SoC's first silicon success, because in the end, problem solving is what we do. Contact us to let us know your most immediate problem in your memory subsystem. Thank you. So before the Q&A session, here's our contact information that you can reach out to our sales and support team. Thank you.